Think for a moment about the word nothing. Not the casual, conversational nothing. Not the nothing you mean when a friend asks what you're doing tonight and you shrug and say nothing. The real nothing. The absolute nothing. A void so complete that not a single particle, not a single photon, not even a whisper of energy could survive inside it. Philosophers have argued for millennia about whether true nothingness is even possible. Empty space, it turns out, is not really empty. Even the darkest, most desolate corner of the universe is threaded through with quantum fluctuations, virtual particles winking in and out of existence, the faint residual glow of ancient light still echoing from the Big Bang. The universe, for all its bleak and enormous spaces, cannot quite manage true nothingness. To appreciate why this matters, consider what it would take to describe the universe's most familiar objects precisely. The surface of Mars, for example, with its vast canyon systems, its ancient dried-up riverbeds, its towering volcanic mountains and sweeping plains of iron oxide dust, would require an enormous catalog of numbers to describe completely. Every elevation, every crater, every boulder field. A planet would require more still, and a living cell, with its interlocking protein machinery, its genetic code, its membrane channels and signaling cascades, would require an almost unimaginable quantity of information to specify with any precision. The more carefully you look at almost anything in the universe, the more detail reveals itself, and the more numbers are needed to capture it all. And yet, scattered across the cosmos, hiding at the centers of galaxies, lurking at the end of the life of the most massive stars, there are objects so extreme, so violent in their geometry, that they have cut themselves off from the rest of reality entirely. Objects from which nothing, no matter, no radiation, no signal of any kind, can ever return. Objects that do not merely occupy space but warp and bend the very fabric of space-time around them, creating a gravitational prison so total and so absolute that the laws of physics as we know them break down at their very hearts. These are black holes, and the question of what they actually are, what happens inside them, what they are made of, and what they mean for the nature of reality itself, is one of the deepest and most extraordinary puzzles in all of science. To understand what a black hole is, we need to begin not in the modern era of gravitational wave detectors and X-ray telescopes, but in the considerably less technologically impressive setting of an English country parish in the late 18th century. Because the seed of the idea, the first glimmer of what would eventually become one of the most profound concepts in physics, was planted not by a professional scientist with access to enormous instruments, but by a thoughtful and deeply curious country clergyman with rather a lot of spare time on his hands. John Michel was the kind of thinker who flourished in the long, quiet hours available to a provincial English parson. By the 1780s, he had already made serious contributions to science. He had designed a delicate instrument to measure the gravitational constant. He had thought carefully about the nature of earthquakes, and he had pioneered the statistical study of double-star systems. But his most startling idea came from a relatively simple chain of reasoning, the kind of thinking that in retrospect seems almost obvious, and yet which nobody else had thought to pursue. Michel began with two facts that were by his day firmly established. The first was Newton's theory of gravity, which by the late 18th century had proven itself the most powerful and precise scientific theory humanity had ever constructed. Newton argued that every object in the universe with mass attracted every other object with mass, and the force between them depended on how massive they were and how far apart they sat. Nothing was immune to this attraction. Planets pulled on moons, stars pulled on planets. Everything pulled on everything else, and the whole grand clockwork of the solar system could be explained and predicted with extraordinary accuracy using this single elegant law. The second fact Michel had to work with was Newton's theory of light itself. Newton had proposed that light was composed of tiny particles, little corpuscles of luminosity, each one a minute package of something traveling at extraordinary speed. This was still a contested idea in Michel's time. Competing wave theories of light had their advocates, but the corpuscular theory had Newtonian authority behind it and was taken seriously. Now here was Michel's critical step. If gravity was truly universal, acting on everything that had mass, and if light was made of particles, then gravity must act on light too. The tiny particles of light must feel the gravitational pull of any massive body they pass close to. And if that was the case, then light emitted from the surface of a very massive object would be tugged backward by that object's gravity as it tried to escape. Whether the light could actually escape would depend on two things: how fast the light was traveling and how powerful the gravitational pull trying to drag it back. This brings in another key concept that Michel had at his disposal: the idea of escape velocity. Every object you throw upward from the surface of the Earth eventually comes back down, pulled back by gravity. But throw something fast enough, and it will escape the Earth's gravity entirely, heading outward forever and never returning. The precise speed needed to do this, called the escape velocity, depends on the mass and size of the object you're trying to escape from. For the Earth, this is roughly 11 kilometers per second. For the Sun, it rises to around 617 kilometers per second. But there is nothing in Newton's theory that places a ceiling on escape velocities. Imagine an object so massive or so compact that its escape velocity exceeded the speed of light itself. In that case, the particles of light emitted from its surface would be hurled upward, slow, stop, and fall back, just as a stone thrown skyward falls back to Earth. Such an object would be entirely dark. It would pull on everything around it with enormous gravitational force. It would have mass. It would have gravity, but it would emit nothing that could ever reach a distant observer. It would be, to use the language of our own time, a black hole. Michel published this idea in 1783, calling these objects dark stars, and the elegance of his reasoning is remarkable, given how little he had to work with. He even estimated how large such an object would have to be, an object with the same density as the Sun, but 500 times larger would trap its own light entirely. He communicated his findings to the Royal Society in London, where they were received with polite interest and then more or less forgotten. This was extraordinary thinking, a genuine conceptual breakthrough, and yet the world simply was not ready for it. Part of the problem was that Michel's picture, though intuitive, rested on a Newtonian foundation that would eventually need to be completely reconstructed. Newton's corpuscular theory of light was contested from the start, and by the early 19th century, wave theories of light had largely displaced the particle picture. If light was a wave rather than a stream of particles, did it have mass? Did gravity act on it in the way Michel assumed? These questions were unresolved, and without clear answers, the dark star concept had no firm ground to stand on. The concept was noted, discussed briefly in a few scientific circles, and then quietly shelved. For over 100 years, it sat there, an intellectual curiosity with no obvious connection to physical reality. Pierre-Simon Laplace, the great French mathematician, independently derived essentially the same idea a few years after Michel and included it in his landmark celestial mechanics text, but later removed it from subsequent editions, perhaps because he too felt the theoretical foundations were uncertain. The drawer would not open again until a very different kind of conflict was consuming the world. The winter of 1915 was not a comfortable time to be alive on the Eastern Front of the First World War. German astronomer Karl Schwarzschild had volunteered for military service despite being in his early 40s, and he found himself stationed in one of the most brutal theaters of that catastrophically brutal war, calculating artillery trajectories by day and turning, when he could, to the extraordinary new mathematical machinery that had just been unleashed upon the scientific world. In November of 1915, Albert Einstein had published his general theory of relativity, and the equations at its heart were unlike anything that had appeared in physics before. Where Newton's theory of gravity described a force acting between masses across empty space, Einstein's theory described something far more geometrical and strange. Mass, in Einstein's framework, did not merely produce a force. Mass and energy and momentum curved the very fabric of space-time itself. What we experience as the force of gravity is in this picture not a force at all, but the result of objects following the most natural paths they can through a curved and warped geometry. The planets orbit the sun not because the sun reaches out and grabs them with a gravitational hand, but because the sun has bent the space-time around it, and the planets are simply following the straightest possible paths through this curved geometry, paths that happen to loop around the central mass in what look to us like orbits. This was a magnificent idea. It was also described by 10 coupled nonlinear partial differential equations of formidable complexity, and finding exact solutions to them seemed to many physicists essentially hopeless. Schwarzschild disagreed. In the appalling conditions of the Eastern Front, riding by candlelight in a military camp while shells burst somewhere not very far away, he found the first exact solution to Einstein's field equations. He was looking for the simplest possible case: a perfectly spherical, non-rotating, electrically neutral mass sitting alone in an otherwise empty universe, and asking what the geometry of the space-time around it would look like. The solution he obtained was elegant, and it was exact. It described how the curvature of space-time varied with distance from the central mass. Far away from the mass, the space-time was nearly flat and gravity was weak. Closer in, the curvature grew stronger. So far, this was roughly what you would have guessed from Newtonian intuition. But inside the mathematics, there was something unexpected. Something that at first looked like a defect in the solution. A place where certain quantities in the equations blew up to infinity while others collapsed to zero. This strange behavior happened at a precise distance from the central mass, a distance now called the Schwarzschild radius. For the Sun, this radius works out to roughly 3 kilometers. For the Earth, it is less than a centimeter. For a typical human being, it is incomprehensibly small, roughly 10 to the power of negative 23 meters, far smaller than a single atomic nucleus. The actual Sun, of course, has a radius of about 700,000 kilometers, so the singularity in the Schwarzschild solution is buried far inside the mass of the Sun, where the solution does not apply. But suppose you could compress the entire mass of the Sun into a sphere with a radius smaller than 3 kilometers. Then something dramatic would happen. That critical radius, the Schwarzschild radius, would mark the boundary of what would come to be called the event horizon. And the event horizon is not a physical surface in any ordinary sense. There is no wall there, no membrane you could touch, but it marks a point of no return. Any object, any particle, any photon of light that crosses inward through the event horizon cannot ever, under any circumstances, return to the outside. The geometry of space-time inside the event horizon is so severely warped that all possible paths through it, all possible future directions for any object that finds itself inside, point inexorably inward toward the center. The singularity at the heart of the black hole is not merely somewhere you will end up if you are unlucky. It is, in a deep mathematical sense, your future. Every direction points toward it. There is no other place to go. Schwarzschild wrote up his solution and sent it to Einstein, who was astonished that an exact solution had been found at all, let alone so quickly and in such difficult circumstances. Schwarzschild would die on the front only a few months later from a skin disease contracted during the campaign. He never knew that his solution would eventually be recognized as describing some of the most dramatic and important objects in the observable universe. For several decades after Schwarzschild's discovery, his solution attracted relatively little serious attention as a description of anything physically real. The idea that a real material object could be compressed into its own Schwarzschild radius seemed fantastical. No known physical process could achieve anything remotely like this. General relativity itself remained something of a scientific backwater during the 1920s, 30s, and 40s, overshadowed by the dazzling revolution of quantum mechanics that was reshaping physics from the ground up. Physicists were discovering the quantum nature of matter and light, developing atomic theory, building the foundations of particle physics, and general relativity sat quietly to one side, beautiful, precise, but seemingly irrelevant to the cutting edge of discovery. Then, gradually, things began to change. In the late 1930s, the physicist J. Robert Oppenheimer and his collaborators showed that a sufficiently massive star, reaching the end of its life, could not be prevented from collapsing under its own gravity to something like the Schwarzschild solution. The pressure generated by quantum mechanics in dense stellar remnants, the mechanism that holds white dwarf stars and neutron stars up against gravitational collapse, has a limit. Beyond a certain mass, nothing can stop the collapse. The conclusion, troubling as it seemed, appeared to be that very massive stars must eventually collapse to a singularity. But this work attracted little sustained interest at the time, and the subject went quiet again through the war years. The real awakening came in the 1960s, driven by a combination of new astronomical observations and a flowering of theoretical insight that transformed general relativity from a quiet corner of mathematics into one of the most vibrant areas in all of physics. Astronomers were discovering strange new objects in the sky, Quasars, enormously energetic sources of radiation at cosmological distances, releasing more energy than entire galaxies from regions scarcely larger than a solar system. Pulsars, rapidly spinning neutron stars emitting regular pulses of radio waves with clockwork precision, were discovered in 1967. The universe, it was becoming clear, was a much more violent and extreme place than anyone had previously suspected. And on the theoretical side, new tools and new minds were arriving. Foremost among the latter was a young British physicist who had recently received a devastating personal diagnosis and who had responded to it by throwing himself into the most difficult problems he could find. By the time Stephen Hawking was finishing his undergraduate degree at Oxford in the early 1960s, he had become a brilliant but reportedly rather idle student, coasting on natural talent rather than effort. That changed abruptly when, at 21, he was diagnosed with a degenerative motor neuron disease and given a life expectancy measured in months. The response to this terrible news, which would eventually prove drastically wrong, as Hawking lived to the age of 76, was to work. To really work, with an intensity and focus that his Oxford tutors had never seen from him. Confronted with the prospect of early death, Hawking seems to have decided that whatever time he had would be spent doing something that mattered. He found a collaborator and intellectual sparring partner of the first order in Roger Penrose, a mathematician of extraordinary geometric intuition who was developing new ways of thinking about the global structure of space-time. Together, Hawking and Penrose proved a series of theorems about singularities, mathematical results of great generality and power, that settled a question that had been nagging at physicists for years. The worry was this: the Schwarzschild solution was perfectly spherically symmetric, perfectly idealized. Real stars are not perfectly spherical. They rotate, they wobble, they have density variations and magnetic fields, and all the messy complexity of real physical objects. Perhaps the singularity in the Schwarzschild solution was a mathematical artifact of this perfect symmetry. Perhaps in a real gravitational collapse, the slightly off-center material would swirl around each other, miss the singularity, and spray out the other side in some complicated but non-singular explosion. Perhaps real stars simply would not collapse to black holes at all. Hawking and Penrose showed with mathematical rigor that this hope was unfounded. Under very general conditions, conditions satisfied by any realistic collection of matter, gravitational collapse inevitably produces a singularity. The result did not depend on perfect symmetry. It did not rely on special initial conditions. If you start with enough matter in a small enough region, a singularity will form. The black hole was not a mathematical pathology. It was a physical inevitability. This theoretical work coincided with the observational discovery of the first strong candidate for a real astrophysical black hole. The X-ray satellite Uhuru, launched in 1970, scanned the sky in X-ray wavelengths rather than visible light, and what it found was startling. The X-ray sky was crowded with powerful compact sources that had no obvious explanation in terms of ordinary stars. One source in particular, in the constellation Cygnus, stood out, Cygnus X1, an intensely bright and rapidly varying X-ray emitter associated with a visible star in a binary system. The variations in its X-ray output were too rapid to be produced by any ordinary stellar object. The most compelling interpretation was that Cygnus X1 was a black hole, an invisible compact object pulling gas from its companion star, heating that gas to millions of degrees in a swirling accretion disk, and converting the gravitational energy released into an enormous output of X-ray radiation. It was not a proof. Science rarely deals in proofs outside of mathematics. But the case was strong, and it would become stronger over the following years as more and more similar objects were discovered. Since those first discoveries, hundreds of black holes of stellar mass have been identified in our own galaxy. In 2015, the LIGO Observatory detected for the first time the gravitational waves produced by two black holes spiraling together and merging, an event that sent ripples through the fabric of space-time itself that were detectable here on Earth after traveling over 1 billion light-years. And in 2019, the Event Horizon Telescope collaboration released the first direct image of the shadow of a supermassive black hole, the monster at the center of the galaxy, M87, some 6.5 billion times the mass of the Sun, surrounded by a glowing ring of superheated plasma. The universe, it was confirmed beyond any remaining reasonable doubt, is full of these things. Here is something that should astonish you. The Moon, as we established in the opening thoughts of this script, would require millions of numbers to describe precisely the location and size of every crater, the chemical composition of the surface in every region, the height of every hill and depth of every valley. A human face, familiar and recognizable, encodes an almost infinite variety of detail in its lines and planes and proportions. A galaxy, with hundreds of billions of stars, each in its own orbit, each a unique object, requires a number of parameters to describe it that defies imagination. A black hole requires three. Three numbers, and only three, are needed to completely specify any black hole anywhere in the universe, no matter how it formed, no matter how large it is, no matter what went into making it. These three numbers are its mass, its electric charge, and its angular momentum, the rate at which it spins. Know those three numbers and you know everything about the black hole that can in principle be known. There is nothing else to know. Every other detail, what fell in to make it, whether it formed from the collapse of a single star or the merger of 100 smaller black holes, whether it consumed ordinary matter or antimatter or the accumulated libraries of 1,000 civilizations, has been completely erased. This result, now known as the no-hair theorem, was proved in the late 1960s and early 1970s through the combined work of several physicists, including Werner Israel, Brandon Carter, and Hawking himself. The colorful name was coined by the American physicist John Wheeler, who had a gift for memorable phrases. He was also responsible for the term black hole itself, which entered common usage after Wheeler began employing it in the late 1960s. The no-hair theorem says that black holes have no hair, no distinguishing features, no individual characteristics, nothing that differentiates one black hole from another of the same mass, charge, and spin. This is extraordinary when you consider the range of ways a black hole can form. Stellar mass black holes, a few times heavier than our Sun, form when massive stars exhaust their nuclear fuel and can no longer generate the outward pressure needed to resist gravitational collapse. The core of the star collapses in a fraction of a second, and if the mass is sufficient, the collapse cannot be stopped. Supermassive black holes, millions or billions of times heavier than the Sun, lurk at the centers of most large galaxies and grow by consuming the gas and stars that surround them over billions of years of cosmic time. Intermediate mass black holes, objects in between these two extremes, likely form through the repeated merging of smaller black holes or through the collapse of very dense stellar clusters. And in the early universe, exotic processes might have produced primordial black holes directly from density fluctuations in the first fraction of a second after the Big Bang. All of these wildly different formation histories, all of these different compositions and origins lead to the same result. The black hole forgets its past. 3 numbers, and the transformation is complete. So what actually happens to an object that crosses the event horizon? What is it like to fall into a black hole? And what, if anything, lies beyond the horizon? The first thing to appreciate is that the event horizon is not, from the perspective of a freely falling observer, a place where anything obviously dramatic occurs. If you were falling feet first toward a black hole of sufficient mass, a supermassive black hole, say, millions of times heavier than the Sun, crossing the event horizon would feel, in the moment, like nothing at all. There is no wall, no bright line in space, no signal to indicate you have passed the point of no return. The event horizon is defined not by local physics, but by the global structure of space-time. By the fact that no future-directed path through space-time from inside the horizon can ever reach the outside. But you cannot know at the moment you cross it that you have crossed it. Nothing locally distinguishes the event horizon from the space just outside it or just inside. What would eventually kill you, given enough time and a sufficiently small or sufficiently massive black hole, in very different ways, is not the horizon itself, but the growing intensity of the tidal gravitational forces as you approach the singularity at the center. Tidal forces arise because gravity grows stronger closer to a gravitating body. So the gravitational pull on your feet, if they are closer to the center, would be stronger than the pull on your head. The difference between these two pulls is the tidal force, and it acts to stretch you along the direction pointing toward the center while compressing you from the sides. Physicists have given this process the memorable name spaghettification. For a stellar mass black hole, whose Schwarzschild radius is only a few kilometers, the tidal forces at the event horizon would be violent enough to spaghettify you long before you reached the horizon. For a supermassive black hole, whose event horizon might be as large as the entire solar system, the tidal forces at the horizon are relatively mild, and you might survive the crossing, only to be inevitably spaghettified as you continue falling inward and the curvature grows more extreme. But regardless of what you experience along the way, the end point is the same: the singularity. A point, or rather a region, since quantum gravity likely changes the picture at the very smallest scales, where the curvature of space-time becomes formally infinite, where the equations of general relativity break down and can no longer be used to make predictions. What happens at the singularity is genuinely unknown. It is one of the great open questions of fundamental physics. Most physicists believe that the singularity is not a real physical feature of the universe, but rather an indication that general relativity, which is after all a classical theory, not a quantum one, has reached the boundary of its validity. A complete theory of quantum gravity, whatever that turns out to be, should replace the singularity with something finite and calculable. But we do not yet have a complete theory of quantum gravity, and so the singularity remains, for now, a wall of mathematical mystery. Meanwhile, for the observer outside the black hole, the story is different in a deeply strange way. Suppose you are watching your colleague fall toward the black hole from a safe distance. What do you see? As your colleague approaches the event horizon, light emitted from them takes longer and longer to reach you, because the light is fighting against stronger and stronger gravitational pull. This has a dramatic effect. Your colleague appears to slow down as they approach the horizon, moving more and more slowly, their light increasingly redshifted to longer and longer wavelengths, growing dimmer and dimmer. From your perspective, they never quite reach the horizon. They appear to hover just outside it, fading away into the darkness as their light grows too redshifted and too faint to detect. From your colleague's own perspective, they cross the horizon in finite time and fall onward toward the singularity. From your perspective, they freeze at the horizon and fade. Two observers, one event, two completely different descriptions of what happens. This is not a paradox. It is a feature of the deeply non-intuitive geometry of curved space-time. But it is a profound indication that the universe does not work the way our everyday intuitions suggest it should. By the early 1970s, as observational evidence for black holes was mounting and theoretical tools for studying them were becoming increasingly sophisticated, a group of theorists, including Hawking, James Bardeen, and Brandon Carter, noticed something remarkable. Black holes, these apparently dead and featureless gravitational prisons, obeyed a set of laws that bore a striking and suspicious resemblance to the laws of thermodynamics. Thermodynamics is the branch of physics concerned with heat, temperature, and entropy. Its laws were established in the 19th century through the practical study of steam engines and the theoretical analysis of gases, and they represent some of the most firmly established results in all of science. The first law of thermodynamics says that energy is conserved. The second law, arguably the most profound result in physics, says that entropy, a measure of the disorder or the number of accessible microscopic configurations of a system, can never decrease in a closed system. It always stays the same or increases. This is why heat flows spontaneously from hot objects to cold ones and never the other way around. It is why you cannot unscramble an egg. It is why time, unlike the spatial dimensions, seems to have a definite direction. What Hawking, Bardeen, and Carter showed was that there appeared to be exact analogues of these thermodynamic laws for black holes. The mass of a black hole played the role of energy. The surface gravity at the event horizon played the role of temperature. And most strikingly, the area of the event horizon played the role of entropy. Hawking had proven that the area of a black hole's event horizon could never decrease. Any process, matter falling in, radiation being absorbed, two black holes merging, would always leave the horizon area the same or larger. Just as the entropy of a closed thermodynamic system never decreases, so the area of a black hole's horizon never decreases. This was initially treated by some as a mathematical coincidence, an amusing structural parallel between two very different areas of physics, but nothing more than an analogy. The temperature was not a real temperature. The entropy was not real entropy. They were just mathematical quantities that happened to obey similar equations. Or so some believed. It was Jacob Bekenstein, a graduate student of John Wheeler's, who pushed back against this conservative interpretation. Bekenstein pointed out a fundamental problem with treating the thermodynamic analogy as merely formal. If you threw a hot cup of tea into a black hole, the thermal entropy of the tea, which represented the vast number of ways the molecules of the tea could be microscopically arranged, would apparently disappear. The black hole, described by only 3 numbers, would have no way of recording what went into it. And yet the second law of thermodynamics was supposed to be inviolable. Entropy was not supposed to be destroyed. The resolution, Bekenstein argued, was that the black hole genuinely did have entropy of its own, and that entropy was proportional to the area of the event horizon. When the tea fell in, the horizon area increased, and this increase in black hole entropy more than compensated for the disappearance of the tea's thermal entropy. The total entropy of the universe, T plus black hole, increased as the second law demanded. The analogy was not merely formal, it was real. This was a striking and controversial claim, but it would soon be given powerful support from a completely unexpected direction. To understand what happened next, we need to think about the quantum mechanical vacuum, about what empty space actually looks like when examined at the finest possible scales. Classical physics describes the vacuum as truly empty, devoid of anything. Quantum mechanics tells a very different story. The Heisenberg uncertainty principle, one of the foundational results of quantum theory, places fundamental limits on how precisely certain pairs of physical quantities can be simultaneously known. The more precisely you know the position of a particle, the less precisely you can know its momentum. The more precisely you know the energy of a system at a particular moment, the less precisely you can know when it had that energy. This second form of the uncertainty principle has a remarkable consequence for the vacuum. The vacuum cannot have a perfectly well-defined energy of 0 at all times. There is an unavoidable uncertainty in the vacuum energy, and this uncertainty means that the vacuum is not empty, but is instead constantly and furiously fluctuating. Pairs of virtual particles, a particle and its antiparticle, are continuously popping into existence from the vacuum energy, existing for the briefest possible instant, and then annihilating each other and vanishing again. This happens at every point in space, at every moment in time, everywhere in the universe. The vacuum is not a quiet void, but a frothing sea of transient quantum activity. Under normal circumstances, these virtual particles simply appear and disappear again without any lasting effect. But what happens to this quantum vacuum in the vicinity of the event horizon of a black hole? In 1974, Hawking tackled this question using a combination of general relativity and quantum field theory. His calculation was technically demanding, and the result was deeply surprising. What he found was that the event horizon does not merely passively separate the inside from the outside of the black hole. It actively transforms the quantum vacuum in its vicinity in a way that produces real physical radiation. The intuitive picture, and it is only a picture, an aid to intuition rather than a precise description of the mathematics, is this. Virtual particle-antiparticle pairs are constantly appearing just outside the event horizon. Ordinarily, they would annihilate each other almost immediately. But occasionally, one member of the pair finds itself on the inward side of the horizon at the moment of its creation. It falls inward and can never return. Its partner is now stranded outside the horizon, unable to annihilate, and must become a real particle. It carries away a small amount of energy and escapes to infinity as genuine, detectable radiation. Where does this energy come from? It comes from the black hole itself. The infalling virtual particle carries negative energy into the black hole. This is a feature of the unusual space-time geometry near the horizon, and this reduces the black hole's mass by a corresponding amount. The escaping particle carries positive energy away. The net result is that the black hole very slowly loses mass, radiating energy into the surrounding space. This radiation, now universally called Hawking radiation in recognition of its discoverer, has a thermal spectrum. It looks exactly like the radiation emitted by a hot body at a definite temperature. And the temperature of this radiation, the Hawking temperature, is precisely what Bekenstein's thermodynamic analysis of black holes had predicted it should be. The Hawking temperature is inversely proportional to the mass of the black hole. This has a counterintuitive implication. As the black hole radiates and loses mass, it gets smaller, and its Hawking temperature gets higher. A hotter black hole radiates more intensely, losing mass faster, which makes it hotter still, which makes it radiate more intensely in an accelerating feedback loop that ends in a final burst of intense radiation as the black hole evaporates completely. The entire process is extraordinarily slow for any black hole of astrophysically relevant size. A black hole of a few solar masses would take an unimaginably long time to evaporate, vastly longer than the current age of the universe. But in principle, given enough time, black holes evaporate entirely. This was a genuinely revolutionary result, not merely because it showed that black holes radiate, that was surprising enough, but because of what it implied about the relationship between gravity, quantum mechanics, and thermodynamics. Hawking radiation was derived from a calculation sitting at the intersection of all three of these great frameworks of physics, and the fact that it gave a finite, well-defined, physically reasonable answer was itself remarkable. It confirmed Bekenstein's conjecture that black hole entropy was real entropy, not merely a formal analogy. And it opened up a question so profound and so troubling that it has occupied some of the finest minds in theoretical physics for 50 years. Here is the problem. In ordinary quantum mechanics, the most precisely tested theory in the history of science, information is never destroyed. This is not a philosophical preference or an aesthetic principle. It is a hard mathematical consequence of the structure of quantum theory. The equations that govern quantum mechanical evolution are reversible. Given the complete quantum state of a system at any moment, you can in principle reconstruct everything about its past, just as you can predict everything about its future. Information is conserved absolutely and without exception. But now consider a black hole. Matter falls in, carrying with it an enormous amount of information, the precise quantum states of every particle, the details of every configuration. The black hole, according to the no-hair theorem, forgets all of this, retaining only mass, charge, and angular momentum. Then the black hole radiates, slowly losing mass through Hawking radiation until eventually it evaporates completely. The Hawking radiation, in Hawking's original calculation, is perfectly thermal, perfectly featureless. It carries no information about what fell into the black hole. The detailed quantum states of the infalling matter are simply gone. This is called the black hole information paradox, and it is a genuine paradox in the technical sense, a logical contradiction arising from premises that each seem individually sound. On one side, you have the principles of quantum mechanics, which forbid information loss. On the other side, you have Hawking's calculation, combined with the no-hair theorem, which strongly suggest that information is destroyed. One possible resolution is that Hawking's original calculation was approximate, and that in a more complete treatment, the Hawking radiation would turn out to carry subtle correlations, tiny quantum mechanical entanglements between different emitted particles that encode the information about what fell in. The radiation would look thermal to any crude measurement, but a precise and exhaustive analysis of every photon emitted over the entire lifetime of the black hole would in principle allow you to reconstruct the original quantum state. The information would be there, hidden in the correlations, not lost. This is currently the favored resolution among most theoretical physicists, but the argument for it is indirect and difficult to make precise. It received strong support from an unexpected direction, from the study of a mathematical structure called the holographic principle, which emerged from string theory in the 1990s. We noted earlier that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. For an ordinary gas confined in a box, the entropy grows with the volume of the box. Double the volume, and you roughly double the number of possible microscopic configurations, and therefore roughly double the entropy. But for a black hole, doubling the radius, which increases the volume by a factor of 8, only quadruples the entropy, because it quadruples the area. The entropy is a property of the surface, not the interior. This is a deeply puzzling result. In everyday physics, information is stored in three-dimensional systems in proportion to their volume. Computers store information in physical media that occupy volume. Brains store memories in neural networks that occupy three-dimensional space. The idea that a three-dimensional system could have its information content limited by its two-dimensional surface area suggests something radical. That the three-dimensional interior might not be as independent of the two-dimensional boundary as we naively assume. In the 1990s, this intuition was given precise mathematical form through the work of Gerard 't Hooft, Leonard Susskind, and most powerfully, Juan Maldacena. Maldacena's 1997 discovery, now known as the ADS/CFT correspondence, or more generally as holography, established a remarkable duality between two apparently completely different theories. On one side, a theory of gravity in a five-dimensional space-time with a particular kind of geometry. On the other side, an ordinary quantum field theory with no gravity living on the four-dimensional boundary of that space-time. These two theories were shown to be not merely analogous, not merely similar in structure, but precisely and exactly equivalent. Every calculation you can do in one can be translated through a specific and precise dictionary into a calculation in the other. They are the same theory written in two different languages. The immediate implication is that the three-dimensional physics inside the gravitational space-time, including any black holes that might form there, can be completely described by the non-gravitational theory on its two-dimensional boundary. Whatever black holes do in the interior, however they form and evaporate, the boundary theory captures all of it. And in the boundary theory, which is an ordinary quantum field theory, information is never lost. The unitarity of quantum mechanics, the principle that guarantees information conservation, holds perfectly and completely. This does not immediately tell us, in concrete terms, exactly where the information goes or how to extract it from the Hawking radiation. But it does tell us, with as much mathematical rigor as physics currently has available, that the information is not destroyed. The paradox is resolved, not by abandoning quantum mechanics or by modifying general relativity, but by recognizing that the geometry of the gravitational interior can be completely encoded on its lower dimensional boundary. The holographic principle is not merely a clever analogy. It is a deep structural feature of how gravity and quantum mechanics fit together. The information that fell into the black hole is, in some sense that we do not yet fully understand geometrically, stored on the horizon itself. As the black hole evaporates, that information is slowly transferred to the outgoing Hawking radiation through subtle quantum entanglements that Hawking's original calculation was too crude to detect. The thermal radiation is not quite random. It is random in the way that a well-shuffled deck of cards is random, apparently disorganized, but with a perfectly well-defined and recoverable original order hidden within it. Everything we have discussed so far applies to black holes in general, to the mathematical structures, the principles, the paradoxes, but it is worth pausing to consider the sheer scale of what actually exists out there, because the numbers involved are staggering. The stellar mass black holes formed by the collapse of individual massive stars are typically between a few and a few tens of times heavier than the Sun. The Sun itself, for comparison, has a mass of about 2 × 10 to the power of 30 kilograms, roughly 300,000 times the mass of the Earth. Stellar mass black holes have Schwarzschild radii of a few to a few tens of kilometers. They are extraordinarily dense. If you could somehow weigh a black hole and also measure its radius and compute its average density, you would get numbers far beyond anything achievable with ordinary matter. But stellar mass black holes are the lightweights. At the centers of most large galaxies, there sit supermassive black holes, whose masses range from millions to billions of solar masses. The black hole at the center of our own Milky Way galaxy, called Sagittarius A star, has a mass of about 4 million solar masses and an event horizon with a radius of roughly 12 million kilometers, about 17 times the radius of the Sun. The black hole at the center of the galaxy M87, the one imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion solar masses and an event horizon so large that our entire solar system would fit comfortably within it. Beyond even these, there are a handful of genuinely enormous black holes, objects sometimes called ultramassive black holes, whose masses approach and even exceed 100 billion solar masses. These are among the most massive single objects in the observable universe. They are found at the centers of the largest and brightest galaxies, objects so extreme that the entire galaxy is essentially an accessory to the central black hole. The lightest known black holes, by contrast, objects identified through their orbital effects on companion stars or pulsars, are only a few times heavier than our Sun. The Hawking temperature of a black hole is inversely proportional to its mass. So while the temperature of a stellar mass black hole is a tiny fraction of a degree above absolute zero, and the temperature of a supermassive black hole is incomprehensibly smaller still, hypothetical very small black holes, if they existed, would be genuinely hot. A black hole with the mass of a large mountain compressed to its Schwarzschild radius would have a Hawking temperature in the hundreds of billions of degrees. Such an object, if it existed, would be the hottest thing in the universe. Of course, no mechanism currently known to astrophysics produces black holes that small. But the early universe, with its extraordinary densities and violent fluctuations, might have. And there are ongoing searches for signs of primordial black holes in astronomical data. If they exist, they have so far hidden themselves well. For all that we know, and we know a great deal, the black hole remains stubbornly, magnificently mysterious at its deepest level. The singularity at its center continues to mock our best efforts at understanding. General relativity breaks down there, predicting infinite curvature in a way that almost certainly reflects the limitations of the theory, rather than genuine features of the physical universe. Quantum effects must become important at some scale as you approach the singularity, and a full quantum theory of gravity is needed to describe what actually happens there. But despite decades of effort by many of the most talented physicists in the world, a complete and fully consistent quantum theory of gravity remains out of reach. String theory offers what is currently the most developed approach. It dissolves the point-like singularity into an extended structure of fundamental strings and higher-dimensional objects, and in specific, carefully controlled mathematical settings, such as the five-dimensional black holes studied by Andrew Strominger and Qumran Vafa in a famous 1995 calculation. It is possible to count the microscopic states of the black hole precisely, arriving at exactly the Bekenstein-Hawking entropy formula from a first principles microscopic calculation. This is a beautiful result. It confirms that black hole entropy is real entropy, corresponding to a real and in principle countable set of microscopic configurations. But the black holes studied by Strominger and Vafa are highly specialized mathematical objects with extra symmetries and extra dimensions not present in our own universe, and extending these results to the realistic black holes of astrophysics remains a major challenge. Loop quantum gravity, an alternative approach to quantum gravity that tries to quantize the geometry of space-time directly rather than embedding gravity in a broader string-theoretic framework, offers its own picture of what happens near the singularity. In this approach, the singularity is replaced by a region of extremely high but finite density where quantum geometric effects dominate. Some calculations suggest that this quantum bounce might allow what falls into a black hole to eventually emerge, transformed, on the other side. Though what the other side is, and whether it is accessible from our universe in any physically meaningful sense, remains deeply unclear. And then there is the question of what the inside of an old, evaporating black hole looks like in the light of holography and the information paradox. Recent work, in particular a series of calculations done in the 2000s and 2020 using techniques borrowed from quantum information theory, and applied to simplified models of gravity, has suggested that the interior of a black hole is far less empty than the classical picture suggests. After the black hole has emitted roughly half its initial entropy in Hawking radiation, the remaining interior and the emitted radiation become so deeply entangled that the naive picture of a smooth, empty interior breaks down. The precise nature of this breakdown, whether it involves a violent disruption at the horizon, a modification of the interior geometry, or something more subtle, is the subject of intense current debate. Different approaches to the problem suggest different resolutions, and at the time of writing, no fully satisfactory and universally accepted answer has emerged. This is, in other words, a field alive with activity, with open questions at every level, with results that constantly surprise and overturn expectations. Black holes have gone from being a mathematical curiosity in a paper written by a dying soldier on the Eastern Front to being observed directly with radio telescopes. Their mergers felt as vibrations in the space-time fabric, their theoretical properties entangled with the deepest questions in fundamental physics. They sit at the intersection of general relativity and quantum mechanics, the two great pillars of 20th century physics, and the fact that they resist our best current attempts at reconciling those two pillars is perhaps the best evidence we have that our current picture of the universe is incomplete. Something deeper is out there, waiting. The black hole has one more profound thing to teach us, and it concerns not physics, but epistemology. The question of what can be known and by whom. Science has always operated on the assumption that the universe is, in principle, fully knowable. There may be things we do not yet know, things that are difficult to measure or to calculate, things that lie beyond our current technology or mathematical ability. But the classical scientific worldview held that there was no in-principle barrier to knowledge. Given sufficiently advanced instruments and sufficiently powerful mathematics, the secrets of the universe could be uncovered. Black holes complicate this picture in a fundamental way. The event horizon is not merely a barrier to our current technology. It is a barrier to knowledge that is built into the structure of space-time itself. Whatever lies beyond the event horizon is, by the laws of physics, permanently and irrevocably beyond the reach of any external observer. No instrument can reach in and extract information. No signal can cross the horizon from inside to outside. The interior of a black hole is causally disconnected from the rest of the universe, hidden not by contingent practical limitations, but by the deep logic of general relativity. And yet, and this is what makes black holes so philosophically as well as physically fascinating, this does not mean the interior is physically irrelevant. It still influences the outside world through gravity. It still participates in the global geometry of space-time. It leaves its fingerprints on the Hawking radiation it emits. And through the holographic principle, its physics is in some sense fully encoded on the horizon, accessible in translation to an outside observer who knows how to read the code. The universe, it seems, keeps secrets. It keeps them behind mathematical surfaces written into the structure of space-time itself, and it encrypts them in the quantum correlations of radiation emitted over billions of years. But it does not destroy them. The information is there. We simply do not yet have the language to read it. Perhaps that is the most important thing to take away from the study of black holes. not the drama of the singularity or the strangeness of the event horizon, but the discovery that the universe is vastly cleverer than it appears. That apparently simple and featureless objects describable absurdly by only 3 numbers, can hide inside themselves the entirety of their history, the complete record of everything they have ever consumed, encoded and preserved in forms we can barely begin to decipher. The universe does not forget. Even the most voracious gravitational monsters, endlessly consuming everything that falls within their reach, carry within them the full accounting of their crimes. We are, in our current understanding, still standing outside the event horizon, peering at the shadow of something we cannot directly see. The mathematics tells us things are in there. The observations confirm that these objects exist in their billions across the observable universe, and the deepest questions of theoretical physics, the reconciliation of quantum mechanics and gravity, the nature of space-time at the Planck scale, the ultimate fate of information, have their best and most extreme testing ground in the study of these extraordinary objects. What is a black hole? It is the most extreme conclusion of gravity acting on matter. It is a region of space-time from which nothing can return. It is a 3-number object hiding infinite complexity behind its featureless horizon. It is a thermodynamic system with real temperature and real entropy. It is a radiating object that very slowly evaporates its own mass away. It is a gravitational encoder of information. It is the place where our best current theories reach their limit and point, with a kind of cosmic insistence, toward something beyond. A black hole is, in short, the universe's way of telling us that we still have a very great deal to learn. You have been watching the entire history of the universe. Thank you for watching. Don't forget to like and subscribe, and we will see you next time.